So we have Eoin Casserly here. He's the principal of Voluta, an international structural engineering consultancy based in the west of Ireland. Voluta is the name of a type of a seashell and a facade detail. As our name signifies, we are guided by the beauty and efficiency of nature and the accomplishments of past masters. This inspiration, combined with deep knowledge of structural principles, geometries, construction methodologies, and the latest developments in material technology, drives us to innovate and strive for excellence. So Eoin has worked across the world with a focus on grid shells, cable nets, and other special structures. And everybody who hear cable nets maybe knows that he was also working for Schleichbergmann. The name of the presentation is The Performance of Glass as Cladding Material in Long-Span Biome Structures. I'm really looking forward. Please, Eoin.
Thank you. So, as Enrico said, I recently started my own company 2 years ago, and this is actually the first project that I got as my new company as a design consultant for Oman Botanic Gardens. So this is going to be probably the largest botanic gardens in the world. It's around 430 hectares, 40 kilometers from Muscat, the capital of Oman, and it's situated in a very scenic area in the Al Hajar Mountains. So there's two main parts I was working on, the northern biome and the southern biome. So two freeform grid shell structures. The northern biome is a smaller one, around 11,000 square meters surface area, and then the southern biome around 17,000 square meters area, and spans for the primary structure of around 70 meters in the southern biome, so quite large. And I'm leading on to basically a question I asked myself while doing this project. So in the northern biome, there's what's trying to replicate the climate and the plants that occur in the north of Oman. So Oman has quite a special level of biodiversity, and the goal for the project was to showcase this to the world. So the northern biome is showing the north of Oman, very dry climate, gravelly soil, and things like olive trees, apricot trees, juniper trees. Very different to the southern biome, which has what's called a kharif season, which happens in the south of Oman from around June until September, and it's a type of monsoon season. So this is also replicated inside of this biome, and both should finish construction next year. So I was curious, as a structural engineer, not my speciality, of how could such different climates be created within two relatively similar structures? So both glass, and obviously there's MEP usage to create the humidity in this one. But it also got me thinking about other projects I'd worked on before founding Voluta. So I'd done quite a lot recently, I suppose in the past 5 years, on consulting on various botanic gardens around the world. And this one, Eden Project in Qingdao in China, is similar in some ways to Oman Botanic Garden, but one crucial difference is that it uses ETFE as the cladding system instead of glass. And so I was curious, how does this affect the plant development? So if we're not designing for humans, you know, I can, as a structural engineer, I can tell a client or an architect, right, we have these material properties, these structural properties, it will cost this much maintenance, all of these things, but I realized that everything I knew from a building physics perspective was geared towards humans. And I looked deeper into the literature on other types of these structures, and I came across this. This is a quote from the horticulturalist who was working on the Eden project in the UK, the first one, and this was built around 2001. And he wrote in a paper afterwards, optimum conditions for some 80% of the plant species we intend to grow in the biomes at Eden are simply not known. And this is only 20 years ago. So I thought to myself, if I was designing a structure for humans and I didn't know if it would kill 80% of them or not, I could be in trouble. So I thought that it would be interesting to look a bit deeper into this topic. And I realized that there wasn't actually a whole lot of literature there, so I decided to step out of my comfort zone a little bit, and since I'm not a plant biologist or anything like this, to look a bit deeper into what exactly the plants need from the structure, from the cladding. And you might ask yourself, because we've talked, especially on this stage, a lot about building less. Why build at all these type of buildings? Because plants can just grow outside in their natural environments. But unfortunately, due to the climate crisis, these type of buildings are actually more necessary. So approximately 40% of the world's plant species are threatened with extinction at the moment. 723 of these are used for medicine. So it's not only a case of losing biodiversity and this is bad for nature. This is also a disaster for humans. So plant species are dying at approximately a rate of 1,000 to 100 or 10,000% greater than would naturally occur. So botanic gardens can serve as kind of a Noah's Ark for these type of plant species. So for me then, this is a good motivation to understand more and to actually build these structures. So they protect from invasive species that you would have in the wild, from overgrazing. And this, on the previous slide, I forgot to say that, sorry, just go backwards. On the previous slide, I forgot to say that this plant went extinct in 2003. And, you know, plant species are dying faster than people can name them, than scientists can name them. So having these research facilities, these botanic gardens, to study them seems quite necessary. And it seems quite necessary that we achieve better than this 80% we don't know how to deal with. And going back to the theme of the presentation, glass greenhouses are one of the iconic forms of glass architecture. So when these were first built in the 19th and 20th century, they were really a vision of what could be done with glass. But if ETFE, the material I just spoke about, can be more efficient, is there still a place for glass? Are these now redundant? And so this is what I hope to answer, or at least provoke the questions on today. So I know there are some people in the crowd there I can see who have worked with ETFE before, but for anyone who hasn't, it's very different to glass. So ethyl tetrafluoroethylene, it's a type of plastic that is inflated. So on the typical system, you'd have this nozzle here to inflate it to somewhere between 200 and 400 pascals, so that it's a pneumatic structure, and everything, the plastic is in tension. And has to be in tension because its membrane, it's so thin, it's generally ranges between 100 nanometers and 300 nanometers. So much, much thinner than glass. So what we might expect from overhead glazing in one of these structures, probably say 6 6 on the lower side, laminated glass, probably heat strengthened, and then maybe 8 fully tempered on top. So 20 millimeters versus maybe 2 or 3. And obviously, because glass works in bending, while ETFE works in tension as a membrane, we can't compare their structural properties like for like. So we'll have a look at some other properties. Densities aren't drastically far off, but because so much less is used of ETFE, we can see that the overall weight will be less. Almost no sound barrier for ETFE because it has almost no mass. The energy absorption is quite similar on both, dependent on coatings. There's very low surface friction on ETFE, so requires less cleaning. Glass is obviously brittle, where ETFE is plastic, and you might be wondering at this stage, are there any benefits for glass? And hopefully I get to these. So also an important thing to look at, long-term loading, where there's obviously stress corrosion in glass from permanent loading, but there's also creep in ETFE, and ETFE is always permanently loaded for the form-finding process because it's a pneumatic structure and higher cost. So going back to what the plant requirements are, visible light transmittance, this is probably the most important. Solar gain has to be controlled, humidification or dehumidification, heat control, linked up with solar gain, shading, UV transmission, and U value. And one interesting thing I found was that while we're designing buildings for humans within the visible light spectrum, the plant light spectrum, or photosynthetically active radiation, is actually much larger. So the most important parts of plant growth of chlorophyll production are in the blue and the red light waves, so sometimes beyond the visible light spectrum from 400 to 700 nanometers. And that's the equation for power. So all of these different aspects need to be taken care of when choosing a cladding system for these biome structures. And all of this light transmittance needs to be gained depending on the plant. And no more bad news for glass is that ETFE actually provides a bit more of this, a bit more in the ultraviolet range, a bit more in the infrared range, and slightly more in the visible spectrum. It could be a good thing or a bad thing when we look at UVB especially. So if we're looking to protect the plants from bacteria, we want to limit the amount of UV, and this, in the sense, glass can come in well. But some plants need the UV to grow. Thermal transmittance, a lot more long-wave radiation passes through ETFE than glass. Of course, both of these, and both glass and ETFE, these can be more controlled by coatings. And when we look at the U values, like with glass, we can make 2 or 3 layers of ETFE cushions, and these tend to perform better than glass. But when we get to the carbon impact, even though the figures here, when we're looking at the carbon impact from ETFE, it's actually enormous compared to glass. So this isn't really the full story, of course, because this is per kilogram, where we're using maybe 20 times more glass than ETFE. per square meter. But as we saw in the last presentation, glass has much more of scope to improve its processes compared to ETFE, which is actually a byproduct from the petrochemical industry. So around 80% of the embodied energy from ETFE is due to byproducts from brown coal and natural gas. So it can't be produced without it. So even though, if we look at, say, a relative embodied energy for two systems which were roughly the same dimensions, so it was 27 by 33.5 meters clad glass roof, one in ETFE and one in glass. We see that the embodied energy in glass in this example is around double of that of ETFE. But there's so much more scope to improve with glass, as we saw in the last speaker from AGC. And so I believe that this is one of the benefits of this. Thank you.